A neural network makes a prediction. It's wrong. It tries again, a little less wrong this time. After thousands of tries, it's nearly perfect. What is doing that learning? That's this episode. This is Forward Pass AI, a series that builds neural network concepts from first principles. We've covered how a network makes predictions, how it measures its mistakes with loss functions, and how Backprop computes the slopes of those mistakes. Today, how does the network actually use those slopes to get better? SGD, Stochastic Gradient Descent, how AI actually learns. A neural network has parameters, the adjustable numbers inside it. Every parameter influences the output. When the network makes a prediction, we compare it to the target. The gap, the raw difference, is the error. Error is signed, positive if we guessed too high, negative if we guessed too low. Loss takes that error and turns it into a single non-negative number, our measure of how wrong we are. Loss is never negative, which makes it possible to minimize. Backprop's job is to compute, for every parameter, the slope of the loss with respect to that parameter. This is the partial derivative, one number per parameter. Each slope tells us two things. The sign tells us which direction would push loss up. The magnitude tells us roughly how steeply loss responds to nudges of that parameter. Backprop hands over those slopes. It does not move any parameters. That's a different job. The optimizer is the rule that takes the slopes from Backprop and decides what move to actually make. Given a slope for a parameter, which direction do we push it? If the slope is positive, nudging the parameter up would push loss higher, so we push the parameter down. If the slope is negative, nudging up would pull loss lower, so we push it up. Either way, we move opposite to the slope sign. The direction is reliable, the magnitude, whether the slope size is a good step size, that we're about to test. We start with the simplest possible loss surface, a parabola. The loss L equals the weight matrix W squared. Now let's test the simplest possible step rule. Use the slope itself as the step size. Bigger slope means farther from the minimum, so take a bigger step. Sounds reasonable. At the weight matrix W equals 5, slope equals 2 times 5, that's 10. Moving opposite the slope by that full amount, the weight matrix W nu equals 5 minus 10, which is negative 5. Now at the weight matrix W equals negative 5, slope equals negative 10. Moving opposite, the weight matrix W nu equals negative 5 plus 10, that's 5 again. We're back where we started. The dot bounces between 5 and negative 5 forever, never reaching the minimum at 0. The slope told us exactly which direction to move, and applying it directly as a step size trapped us in an infinite loop. We need something else. The fix: don't use the slope magnitude as the step size. Instead, introduce a separate scaling knob, eta, the learning rate. Eta is a small positive number we choose. The update rule becomes the weight matrix W nu equals the weight matrix W minus eta times slope. In other words, take a step in the opposite direction of the slope, but scaled down by eta, not by the slope itself. At the weight matrix W equals 5, slope equals 10, eta equals 0.1. The weight matrix W nu equals 5 minus 0.1 times 10, that's 4. One small step down. Next step, the weight matrix W equals 4, slope equals 8, eta times slope equals 0.8. The weight matrix W nu is 3.2, and so on smoothly toward 0. This rule, subtract eta times the slope, applied once per parameter per step, is vanilla. Stochastic Gradient Descent, SGD. The slope we've been computing is the gradient, that's the g in SGD. Let's write SGD in pure Python. No library, 10 lines. The math is the code, 2 functions. Loss of the weight matrix W returns the weight matrix W squared. Slope of the weight matrix W returns 2 times the weight matrix W. These are exact derivatives, no autograd, no magic. Then the loop. Start at the weight matrix W equals 5, eta equals 0.1. Each step, compute the slope, then subtract eta times slope from the weight matrix W. That's the full update rule. The output shows the weight matrix W walking steadily towards 0 from its starting value of 5, 4, 3.2, 2.56, 2.05 each step, multiplying the weight matrix W by 0.8. By step 19, loss has dropped from 25 to essentially 0. The single line update subtract eta times slope did all of that. Now a real example. We have 5 students, each studied a different number of hours, and we recorded their exam scores. Our model says predicted score equals the weight matrix W times hours plus the bias B. 2 parameters, the weight matrix W, the slope of the line, and the bias B, the intercept. Both start at 0, the network knows nothing yet. Loss is mean squared error, the average of the squared gaps between predicted and actual scores. Formally, the loss L equals 1 over n times the sum of the quantity predicted minus actual, all squared. In other words, we average how badly we missed each student, penalizing bigger misses more. Let's compute one step by hand. At the weight matrix W equals 0 and the bias B equals 0, our prediction for every student is 0. The error for student 1 is 0 minus 40, negative 40. The slope with respect to the weight matrix W, that is, partial the loss L over partial the weight matrix W, equals 2 over n, times the sum of each error times the variable x, plugging in 2 over 5 times the quantity negative 40 times 1, plus negative 55 times 2, and so on. That gives negative 480. In plain terms, loss is falling steeply with respect to the weight matrix W, because our predictions are too low and the variable x is making the gradient large. Partial the loss L over partial the bias B equals 2 over n times the sum of the errors, negative 140. Loss is also falling with respect to the bias B, but more gently because the bias B doesn't get multiplied by the variable x. Now the SGD update, with eta equals 0.01, the weight matrix W new equals 0 minus 0.01 times negative 480, that's positive 4.8. The bias B new equals 0 minus 0.01 times negative 140. That's positive 1.4. After one step, both parameters have moved in the right direction. Now the full implementation, 3 helper functions and a loop. X, S, and Y's hold the 5 data points. Predict returns the weight matrix, W times the variable x, plus the bias B. Miss loss averages the squared errors. Slopes computes both partial derivatives. The loop, start the weight matrix W and the bias B at 0, eta at 0.01. For each of 2000 steps, compute both slopes, update both parameters. That's 2 subtractions per step, the complete SGD implementation. Here's what happens over 2000 steps. Step 0. The weight matrix W and the bias B both 0, loss 5350. Step 1, the weight matrix W jumps to 4.8, the bias B to 1.4, the step we computed by hand. By step 5, the weight matrix W has already reached nearly 15, almost the true answer. Loss has dropped to 420, the bias B is still at 4.5, far from 25. Notice the gap, same eta, but the weight matrix W is converging much faster. Step 100, the weight matrix W has overshot to 18.8. The bias B has only reached 11. Step 1000. The weight matrix W has settled back near 15.2. The bias B is catching up at 24.3. Step 2000. The weight matrix W equals 15.01. The bias B equals 24.98. Loss 0.0001. The model found, predicted score equals 15.01 times hours plus 24.98. The true line is 15 times hours plus 25. SGD got within 1/100th of the true answer in 2000 steps with 10 lines of pure Python. For reference, this is the library equivalent in PyTorch. Optimizer equals optim.sgd, passing in the weight matrix W and the bias B, learning rate 0.01. Then 0 grad, forward pass, backward pass, step. The library is doing exactly the same arithmetic. The pure Python version just makes the math visible. SGD found the line as the trace showed, but look at how unevenly it got there. The weight matrix W reached 15 by step 5, actually overshooting to nearly 19 before settling back. The bias B was still at 4.5 at step 5 and only reached 25 around step 1000. Both parameters use the same eta, but the slope with respect to the weight matrix W gets multiplied by the variable x, which ranges from 1 to 5. The slope with respect to the bias B doesn't get that multiplier, same step size, but the gradients have different natural magnitudes. Applying one step size to parameters with different natural scales is a structural mismatch, not a tuning issue, a design issue. What if every parameter could have its own step size? Let's recap what we built today. Backprop computes one slope per parameter, the partial derivative of loss with respect to that parameter. The optimizer is the separate rule that takes those slopes and decides how to move. SGD's rule, the weight matrix W nu equals the weight matrix W minus eta times slope, move opposite the slope, scaled by eta. That one line is the complete update. Eta, the learning rate, is a critical knob. Too large, the parameter oscillates and never converges. Too small, training is needlessly slow. Right value, smooth descent, and SGD has a structural weakness we saw in the data. One eta for every parameter, even when different parameters have gradients of very different scales. We saw one weakness, same eta for every parameter, even when gradient scales differ, but SGD has more. When the loss surface forms a narrow ravine, a long steep valley, SGD's gradient points sideways toward the wall, not along the valley floor. The result is zigzag descent, slow progress in the direction you actually want, noisy oscillation in the direction you don't. On flat regions and saddle points, where the gradient is tiny, SGD barely moves, sometimes near stationary for thousands of steps. Each failure has a targeted fix. Next episode, momentum. Instead of using only the current slope, we accumulate velocity along consistent directions. That damps the zigzag and accelerates through flat spots.